will move into multi-level or hierarchical or mixed effect models, right? So what's the point of multi-level modeling, right? The first and crucial point of multi-level modeling is the reason for which we call it multi-level or hierarchical is that we introduce structure, that is multiple levels in our parameters. For instance, we have the beta, that's the difference by register, whether articulation is higher or lower in infant-directed speech compared to adult-directed speech. And here we have several levels in the data for the way in which we've constructed the experiment, right? There is an overall mean difference, which we usually call the population level estimate. But there is also a difference within each participant. Each mother in the corpus was talking to their child at one time point and talking to an adult at a neighboring time point, right? Which is what we usually call a within subject contrast or within subject repeated measures, right? Well, said that already. And what we want to do now is to add these levels into our models. Right, because before we conveniently forgot to do so, but this, there's stuff. This is stuff that we know about our data and that we should account for. So, why should we do that? The first is simply that we want to account for the fact that there's repeated measures, right? 2 data points, right, from the same person should not account as much as 2 separate persons. Right, people. So this is especially crucial in frequentist statistics, where, for instance, the p-value is calculated according to the degrees of freedom or the number of data points if they're independent. If there's repeated measures, not all data points are independent from each other, so you need to accordingly reduce the number of degrees of freedom, and that affects your significance testing quite severely. But also in estimation, because as we will see, data points belonging to the same persons are taken into account together. Another reason for using multi-level modeling is that we might be interested not just in the population level effect, but also in modeling individual level effects. This is crucial in studies of individual differences, right, where we are interested in estimate for different parameters for the single individuals that they can be within the same model or separately be, let's say, correlated with another aspect. Let's imagine that parenting attitude is a key aspect in how much parents hypo or hyper articulate. That is, what they think a good parent should do has an effect on the way in which they change their behavior when talking to their child, right? We need to keep the individual level in the model so that we can see whether that's the case, right? But more intriguingly, what multi-level modeling does is partial pooling. I'm going to spend a few slides on partial pooling because it's something that is often neglected when discussing repeated measures. But it's really a cool and powerful aspects of multi-level modeling, right? What is partial pooling? Partial pooling means that we are not taking the data at face value, right? That we know that whenever we measure something, there's noise or idiosyncrasies in the data, right? So for instance, the different mothers that we talk to might or might not have had coffee that morning already. That might affect the data, right? Some of them might have had a good night of sleep, which is quite rare and for a parent, and that might affect the way that they're talking to their child, right? One of them might have a cold, and that might affect the way that they're talking to the child and to the experiment, right? So we shouldn't believe that the measurements that we're doing are a measure of the true phenomenon that we want to measure. They are an imperfect indication. So given that we have 24 measures, 48 measures, or 24 different parents, we can actually rely on the fact that we have several parents to reinterpret the data from any given parent, right? Partial pooling means that we adjust each participant level data with what we learn from the other participants, pulling them towards the mean, right? Because if we have a participant that is very different from the others, right, we might suspect that that's due to random noise, right? To something in the measurement that is not representative of the participant on a more general base, or something in the participant that is not representative of the general population. Right? And usually, right, in some frameworks, you would also talk about checking the data and excluding the outliers, right? But here, what we're doing is we're doing partial pooling. That is, we adjust the data from each participant according to what we learn from the other participants. And these is done in a weighted fashion, meaning that the more outlying the cluster or participant is, the more it gets shrunk towards the mean. We're going to see plots right now. I just want to get the words and concept in place. But also that if one participant has fewer data points in the cluster, right? So it has fewer repeated measures. It's not the case in our example, but it might happen that for some participant we have 4 sessions and for some 2, right? The adjustment would be proportional to how few data points there are. If there are fewer data points, it gets adjusted more because we can trust the data less. If there's a lot of data points, it gets adjusted less. And by the way, this partial pooling is not something that's specific to Bayesian statistics, right? It's a very Bayesian concept, but it's something that happens in any multi-level model. Why are we doing this? Well, we're doing this because our inferences are trying to build generalizable estimates, right? A multi-level model is aiming at giving you better inference for the specific cluster, right? So we know that participants might behave oddly on one condition for whatever, right? The microphone was crappy and we didn't listen to the data. They didn't get coffee that morning. They slept well that morning and they were different from others. See you, Micah, just a second. And therefore we can correct from what we learn from the other participants so that when next time the participant behaves in a way that is not as extreme, we'll be better at predicting. But also, a multi-level model is aiming at giving you a better inference for the population level estimate. Right? If you have few participants that behave very differently, right, they might skew your inference in a way that doesn't describe well neither the normal typical participants, the one in the centers, nor the outliers. Right? It's going to assume that the population is somewhere in the middle where maybe there's nobody. Yes, Micah?
Just a small question on, sorry, just a small question on pooling.
Yes.
So I kind of understand intuition, like at a group level where, you know, it can basically pull outliers towards the estimated mean. I'm curious about how it works with within subject data. Like we have an experiment with 100 trials and however, you know, 100 people and 100 trials. Is it also doing pooling? I don't know how to put it, like, you know, in my 100 trials, most of my reaction times are around some mean for me, but then I have one trial where I wasn't paying attention or something. So is it also helping to finesse or even just leverage that extra data from within each subject? So I guess I could put it a simpler way, like, are you getting pooling both for the between subject estimates that are somehow influenced by the within subject information and vice versa? Because of course, the old way of doing it, we throw away all those 100 trials and their inter-trial variability.
So it depends on the structure of the model, right? So at this stage, it's assuming that your participant, right, will have a given distribution, let's say a log normal or a gamma if it's a reaction time, right? And those outliers will just be part of the estimation of that, right? And then it's the full distribution, the parameters of the distribution that are pulled towards the mean. But let's say that you had 100 different stimuli, right? You could put a random effect for that. So you would add an additional layer to the model, and then they would be pulled towards each other. If you don't specify for each trial a separate random effect, what you're telling the model is that they're interchangeable, right? So that they should be treated, all of them, equally.
Does that mean that, for example, using that same example, like let's say, so for example, oftentimes we exclude trials that are maybe less than 50 milliseconds because they're assumed to be erroneous button presses or just missed trials in general. Would that mean that you'd have a benefit to specify a random effect for the missed trials to keep them into the overall model?
Well, okay, I think that there's, I would go the other direction, right? So sometimes we say, if we have trials that take more than 2 seconds, right, it's likely that the subject got distracted. And here, there could be a good reason for keeping them in, but doing regularization. If you have reaction times that are implausible, right, 50 milliseconds, unless it's a really, really special experiment, is not a realistic reaction time, right? What you could do, and what I think it's quite interesting, is do a mixture model where you're saying that the single data points or the performance of the participant is a mixture of 2 separate distributions. One is the log normal or gamma, that's what you're usually interested in, and the other is, let's say, a normal distribution. Sorry, not a normal, uniform distribution of when the participants get distracted and, oh, go and click. And that actually gives you also a parameter estimate for each participant in terms of how likely they are to get distracted, which might be interesting in, for instance, cognitive performance. I have an example in my class where we look at different kinds of apes and monkeys playing the matching pennies game. Like, where's the penny? In their case, it's where's the grape raisin, right? And we use a mixture model of shifted log normal and a uniform distribution to assess how on task the different species of monkeys and apes are. And that's actually quite interesting, right? Instead of just throwing away a bunch of data points. Of course, that makes the modeling more difficult and time consuming, but you might get some value out of that.
That makes sense in the spirit of trying to model everything you know about that you can get more information. Thanks.
Yeah, and I think that when we do cognitive testing, right, the ability to stay on task instead of getting distracted is something that's meaningful, right? Cool. So let's go and look at our data to see how these levels look in the raw data, right? We're not modeling it yet. So on the left, you see the adult-directed speech, vowel articulation. On the right, and sorry, on the left, you see the population level raw modeling of our data, where you get all the data points for each participant in 2 columns, one for ADS, one for IDS, and then you get simply what ggplot makes as a difference between the 2, right? A linear model of the difference between the 2. On the right panel, what you see is instead the participant by participant data, where you can see that the average effect across all the participants is roughly describing many of the participants, but not all, right? We can see some participants that are contrarians, right? They're going all the way the opposite or they are hyper articulating their child-directed speech, their infant-directed speech, as we would expect from non-Danish participants, while the majority is hyper-articulating. And we also get a few of the participants who are severely hyper-articulating, right? They're really dropping their articulation when they're speaking to their child, right? And it's these interplay between what happens in the individual and what happens at the level of the population that we're trying to model in meaningful ways in the multi-level modeling. So if we turn it into our little graphical notation, this is what we had before, right? We had that the outcome or articulation space is modeled as a normal distribution with a sigma that is the expected average error once we take into account the mean. The mean is defined as a linear model where there's an intercept and an effect of register. But we also added an I index, which is telling us that now we want to allow each participant to have a separate intercept, that is a separate vowel space articulation in ADS, and a separate slope, that is a separate change in articulation when they switch and talk to their child. And this is how it looks like, right? So we have a separate slope and a separate intercept for each participant. And each of them have their parameters, mu1 and sigma1 for the intercept of participant 1, mu2 and sigma2 for the intercept of participant 2, and so on and so forth. However, right, if we stopped here, what we would be doing would be roughly a model of a participant at a time, right? Which is what, at least a few years ago, most neuroimaging studies were doing, right? They were analyzing the effects at the individual level, and then they would do something with these individual level estimates. But here we want to add already at this stage, when we take the individuals into account, partial pooling, right? Whoops. So we are saying that all of these participants are actually belonging to the same population, that they're all part of the same distribution, right, of a population level estimate. Right. And it's at these level that we then add the priors for the mean and the standard deviation of the population level intercept, for the mean and the standard deviation of the population level slope by register, difference by register. Right, so this is the basic idea, right? We're going to keep hammering at these issues from different angles so that you can get an intuitive understanding of what this means. Right. So what we do in BRMS code is we create a third formula where we have articulation as a function of 1 plus register, but then we say that 1 plus register can actually vary by participant, right? 1 plus register over ID. ID is the participant ID. We're saying that those parameters are actually allowed to be different in every single participant. So how does this differ from saying, for instance, articulation is a function of ID? If we were to say that articulation is a function of ID, we would have a separate, completely independent estimate for each participant of the articulation. By using this notation, what we're saying is they don't have a completely separate estimate because they all belong to the same population. We have a fixed effect, which is the population level parameter, and the individual variations are sampled from that effect, are part of that distribution, and therefore they should be partially pooled. Again, there's more slides on this, so don't worry. So the parameters intercept and beta for register have levels, right? The population, what is the mean of the population? If we went and collected a new bunch of mothers, what should we expect to be the mean across them? And we have two parameters here that we need to define, like intercept at the population level and beta at the population level. We have a variation from this mean of the population. That's the group level. We expect individuals to deviate from that. They're not going to be exactly the mean, right? What is the expected deviation? The expected error if we try to predict the mean of a participant from the mean of the population. And that's the sigma for the intercept at the population level and the sigma of the beta at the population level. And finally, we have the individual level, right? We expect each individual to have its mean. And here we're going to have the intercept ID and the beta ID. These are the parameters of the model. So again, since the model is starting to get complicated, right? For instance, we could start wondering, should we put a prior for every participant? Right? We rely on BRMS to tell us what are the priors that are most meaningful to give. We give it the formula, we give it the data, we give it which family we are using, which likelihood function. Three of the parameters are the same as before, right? We have the intercept at the population level, we have the beta at the population level, and we have the sigma total, the average error once we know everything else. But we also have two new parameters. We have the deviations of the participants from the intercept at the population level and the deviation of the participants from the beta at the population level, right? The sigma for the intercept at the population level and the sigma for the beta at the population level. And we need to put new priors there. So what do we put? Well, putting a prior for the deviation that single participants have from the population mean is always a bit tricky, right? But again, we can rely a bit on what we know. This is a standardized scale, right? So we can be roughly liberal and say we expect that participants might vary, one or two standard deviations from the population mean, because that would still keep us within the rough -3 + 3 or -6 + 6 kind of distribution of outcomes that we have discussed. So what I would do is I would start simply with putting for both parameters a prior that is distributed as a Gaussian distribution with a mean of 0 and a standard deviation of 1. Right? So that we allow quite some variation, but still not infinite variation of the participants from the population. And then we're going to check them. So putting the numbers in our graphical model here. And then we do predictive checks, right? When we run these, this is the prior predictive checks. And we see that now it goes a bit broader than before, roughly between -10 and +10, right? Before, I think the last model we tried was between -6 and +6. And this is because we are allowing participants to deviate from the population mean. We're allowing for more heterogeneity in the data. And once we run the data, again, we see the usual pretty decent fit that we started seeing yesterday. This is the posterior predictive check, right? So we can see that our additional priors don't seem to, our additional parameters and priors don't seem to have messed up our inference, right? We can also check how it looks like by participant. Sorry, not by participant, by register. And we see that the picture hasn't changed that much compared to before. And we can check our prior posterior updates, right? You can see the first two and the last one are exactly the same as before. Or there's some small changes, but not really huge. The qualitative aspects and the quality checks that we can do give us the same results. And we have added a third plot. We see in blue the prior, right? It goes from roughly 0 because an error cannot be lower than 0. And it goes all the way up to, 3, maybe 4 for the most extreme. And when we look at the posteriors, we see that the deviation, the average deviation that participants have in terms of intercept and slope, right, is much more constrained than that. The model could learn a lot from the data. The posterior is more peaked than the prior. And that I think it's about 0.5 for one and 0.7 or 8 for the other. Right. So here I don't see any problem with keeping in mind the discussion that we had yesterday about the beta parameter. Right? That some people might think that we're being too conservative for the prior for the beta, but I think it's a good thing to be regularizing, avoiding overfitting to your data. Good. Questions so far? So we're checking the model, right, before we go and look at what it has estimated. And once we go and look at the estimates, we're going to see what it has done in terms of partial pooling. But are there questions on the quality checks of the model? So I can see there's a chat. Yes. Okay. So I'll just move on, and you can also ask questions at a later stage. So we want to assess the contrast, right? We've seen in the former model that the estimate was about minus 0.36 and the estimated error was 0.121. When we do the multi-level model, what we get is a slightly higher, slightly more confident estimate. It's minus 0.39 with a standard error of 0.2, right? Nothing, reliably different, but it seems it shrunk a bit its estimate, right? But the interesting, or we can do the robustness check, right? So again, we change the standard deviation of the slope prior, and the shape is more or less the same as before, right? We're seeing that we're not in the stable area of the estimate, but we might be okay with that if we believe in regularizing our estimates, especially giving the limited amount of data points. We can look at how things have changed from model 2 to model 3, right? And what has changed is that in the multi-level model, right, there is a slight movement towards lower estimates, towards more negative estimates, towards more hypoarticulation, even with the very regularizing priors. But again, it's nothing really to write home about. If you look at the 0.4 on the x-axis, you can see that a standard deviation of 0.4 in the multi-level model is already minus 0.5, while in the model without the random effects is slightly higher, right? So we gain a bit more confidence in the hyperarticulation effect. Sorry, wrong directions. But the cool thing is that we can start assessing these contrasts also at the individual levels, because now we have estimates of the slope of the different for each individual. And we can see here, right, where they are. You look at the final posterior probability, you can see that there's few of the participants that have you know, a canonical threshold certainty of 95%. There's still a few, but that's because we have only 2 data points per participant. And this is, I think, a quite useful testing that you can do, because it allows you not only to say the population level is significantly different, but it allows you also to say these many of the participants were reliably displaying the effect. So it gives you a much more fine-grained perspective on whether the population level effect that you're seeing is something that you should expect to observe in every participant, and what's the proportion of participants that you should expect to see like that. Are you noticing anything weird in this?
I don't know if it's that, but I have a question.
Yes.
Because I'm a little bit confused that the posterior probability, if I remember right from yesterday on the population level, was like 96%, but almost all of the subjects, except for 1, 2, are below 96% here. So what gives rise to this discrepancy?
Yes. So this is the uncertainty, right? In having only 2 data points per participant, we cannot be super certain about the difference being reliable, right? Because the more data points we have, the more confident we can be in shrinking the effect, right? In making it more confident. But if we only have 2 data points, we need to keep the uncertainty. But as we aggregate data across all the participants, right, our population mean is going to be much more confident than the estimate for any given participant. Meaning that we say de facto, well, for any specific participant, we cannot be 100% sure that they're really showing hypoarticulation because we've only observed 1 child-directed speech instance, for instance. But since we see these repeatedly across 24 participants, even if our estimate for any given participant is not certain, our estimate for the population is quite certain.
Yeah, that makes sense. Okay.
This was a good question, right? Because this is really trying to understand what these estimates mean. So one of the things that I note here is that before we were seeing at least a couple of contrarians. So people who were hyper-articulating the vowel space when speaking to children. While here we don't see any, like there is the very first who has something that's very close to 0. Where have they disappeared?
They've been shrunk.
Yes, exactly. We're doing partial pooling. And what we're going to do in the next few slides is to try to see whether this is meaningful. Right? What is this partial pooling actually doing? And should we buy into that? Because we should always be skeptical. So remember the data, right? We had the population mean that goes into one direction and that is preserved, but we also had participants that were going positive. Right? And I'm okay with those that have a very small slope to be shrunk towards 0 or negative. But for instance, there is a very big one. It's the 4th from the top or 5th from the top on the left, has a very decided positive slope, right? And I'm a bit disappointed that these has completely disappeared in the individual level estimate. And this is really what I do when I do my analysis, right? I try to dig into the model and what it's telling me and in which ways it's shaping the data. So to understand what's going on, here I made a panel plot, 1 panel per each participant. In the red line in each participant is basically, the plot on the right, right? It's the row estimates. The blue line is the model that we did yesterday, right? It's pooling across all the participants without considering any difference. It's the model that completely forgets that there are several participants. It thinks that they're all the same. And the green is what our multi-level model is doing. And you can see that in many cases having a very small effect, but for instance, in the very first one, AF, right, it's basically pulling the raw data so much towards the mean that the effect is all but disappeared. Right? And the model is completely agnostic about the direction, right? So if you look at the plot just below JA, the row effect is very big, but it gets pulled towards the mean and it becomes a smaller effect, a much smaller effect. Right. So this is what the multi-level modeling is doing. This is what the partial pooling is doing. Another way, which I think once you've seen this, it's very effective to represent the partial pooling is this. So you can see in the so the x-axis is the intercept estimate, the y-axis is the slope estimate. You can see the outer edge with the the green dots are the row estimates for each individual assessed individually. And the arrow points towards orange dots, which represent the estimates in the model. So you can very clearly and intuitively observe the shrinkage, the pooling. The further these points are from the population average, the more the participant estimates get shrunk there. And again, you can see very clearly that there is no bias in terms of the direction. It's shrinking the big negative effects and it's shrinking the positive effects. In the center, you can, if you squint enough, see the purple-pink dot, which was the model we did yesterday, and the violet dot, which is the new average after the shrinkage, right? Where the more extreme data points are having a smaller effect because we penalize them more. Does this make sense? Right. This might be a problem, right? So for instance, depending on which kind of population we're observing, right? Let's say we're observing psychiatric patients, we might want to preserve more of the diversity. Or we might wonder if this is a problem and we want to dig deeper. Also, as you will run the model, the model will also warn you that there were 12 or whatever number, because it's a probabilistic process, you might get different number, divergent transitions after warm-up. Something is gone wrong as the model is trying to estimate the population mean and the individual effects. There's something that's not really working well, right? And that's what I meant yesterday by saying that the model fails often. What we should do now, right, depends a lot on the science. It's not a statistical question in a pure sense. It's a scientific question, right? For instance, do individual variations of the size of the extremes make sense, right? Are we doing enough in modeling the generative process underlying the data? That is, should we include predictors of the variability? I told you that parenting attitudes might play a role. That's something that we're actually working on. We're not sure yet, but as you probably know, or if you don't, you learn it now. When you have a child in Denmark, the state sends social workers to check that everything is all right, to answer your questions, to provide a shoulder to cry on, and that sort of things. And many of the social workers that I spoke with they have strong opinions about what they call baby language, baby speak. That is, that speaking in simplified words, or calling a train the tutu and the dog a woofie, is a bad thing for your child development. And we suspect that parents buying into these specific position might overgeneralize also to the more prosodic and articulatory ways of talking to the children, right? So we might measure that and see whether that helps us better modeling the heterogeneity of the speech, right? Another thing that we could consider is how much do we trust our data, right? How robust is their measurement? For instance, Chris and I went through the data and did an automated coding of the vowel space, right? But maybe we should go back and code it manually to make sure that the automated algorithm is measuring the right things. The second thing that we could consider is whether one data point per condition is providing enough evidence, right? Maybe we should go back and collect more repeated measures to make sure that the estimates of the individual participants are more robust, right? So these so-called problems with the model actually should be better, should lead us to better rethink how we're running our study. Another thing that is easier to do at this stage on more of a statistical perspective is we can change the likelihood, right? The Gaussian distribution is, shrinking rapidly in the tails. It's a distribution with short tails, has little patience for people who are more different than 3 standard deviations. There's an alternative distribution which is more friendly to so-called outliers, which is the t distribution. Right. What the t distribution does is it has longer tails, so it can fit decently distributions with very diverse participants without having them overly affecting the mean and the standard deviation. So what we do is we might simply change from family Gaussian to family student, right? And what we'll see is that our estimates are changing quite drastically. For instance, they're going to go from minus 0.39 to minus 0.64, right? Still overlapping, but decidedly becoming more negative, and the divergences are going to disappear. However, you can see on the left the estimates of the individual estimates according to the model we run with the Gaussian distribution. On the right, the individual estimates according to the model that is using the student distribution. The positive effects are still disappearing. The plots are very similar. So what to do next? Well, what we would need to do is to model, for instance, what we think might cause the difference. I already mentioned parental attitude, but it could be other sources of, for instance, we could measure dialects that the different mothers are speaking, and so on and so forth. We should go back to the drawing board and think, given the knowledge that we have of this domain, what could be the causal mechanism of the variation? We could also assume, I don't think the data warrants it now, but it's a fun direction, assume that there is a mixture of population, right? So there's 2 populations, one is hyperarticulators and one is hypoarticulators. Or one is a population of people who, whenever the social worker asks them to not use baby language, they do the opposite. and another population of people who follow the rules. And this would mean modeling the outcome as a mixture of two Gaussians instead of just being one Gaussian. In this mixture model, each participant would be estimated as having a certain probability to belong to each Gaussian, and each Gaussian would also be estimated from the data, right? We just say to the model, there's two different Gaussian distributions. You estimate their mean and standard deviation, and you estimate the probability that any given participant belongs to mixture 1 or mixture 2, right?